So now this brings us into what's really happening in the kidneys when all of this is happening. So we went over some general stuff about reabsorption before, where we have this osmolarity gradient, this concentration gradient that's really important, and we, in the descending loop of the loop of Henle, we lose water from the filtrate, which is so water is reabsorbed from the filtrate back into the intracellular fluid and then the blood. And then on the ascending loop, we reabsorb salt. And then we get to this collecting duct. And that's something that's going to be really important here. I want to remind everybody about the importance of this counter current in the vasa recta that's maintaining the loop of Henle and the concentration gradient. But we need to talk about ADH and vasopressin and what's going on here. So we've come to this a couple of times, we've brushed over it, we haven't really talked about what exactly is actually happening in the kidneys. And this is where we get to that collecting duct. So the collecting duct, which if you remember is still running through that concentration gradient and going down, well, we can determine how much water is going to be reabsorbed in that collecting duct by whether or not we open aquaporins to let water out of the filtrate and back into the bloodstream. So when ADH is not present, there are few or no aquaporins present in the cell membrane between the cells of the collecting tubule wall and the lumen where the filtrate is. And this lets very little water through, even if there's a big concentration difference. However, when ADH is released, that causes a whole lot of aquaporins to be taken from these aquaporin storage vesicles inside the cell and moved into these membranes. When it's moved into these membranes, that's going to allow water to flow down the concentration gradient from the filtrate into the cell and then into that very concentrated extracellular fluid and then the plasma. So when ADH is released, that causes more reabsorption of water in the collecting duct. So to sort of see that here we've got the loop of Henle is going to be doing the same thing no matter what. When ADH is present, we've got lots of aquaporins. As it goes into this more concentrated medulla, more water will be taken out, and we wind up with a small volume of concentrated urine. When there's no ADH present, then no water is leaving from this filtrate in the collecting duct. So you've got this very dilute filtrate that was produced up here in the distal tubule, and so nothing is going to change. It's going to go directly out as it is, producing a large volume of dilute urine. So if you remember our chemical Eric patient in that case study, why he kept having to go to the bathroom a lot during the middle of the night was because he was producing this large volume of dilute urine. The body wasn't reabsorbing any of that water. In most normal situations, you have some ADH in your system. And so you're going to reabsorb some, but as long as you're not dehydrated, you're not going to be maximizing that. And so this is very variable, and it can change depending on very fine gradations of vasopressin or ADH. So you can, your body can manipulate this to exactly the level that it needs at the time. All right, and if you remember now, here's back to our renin, angiotensin, aldosterone system, and that is our ADH down here that was being stimulated by angiotensin 2 for the pituitary to produce ADH, causing this absorption in the collection duct. So all of that's fitting back into this big system that we keep looking at. Now, one thing that can be important to talk about here are diuretics. Diuretics are drugs that increase urine production. Now, when you think about this, you need to be thinking about why would we want to increase urine production? I'm not going to answer that for you, but I want you to think about what would be the benefit to increasing urine production. What does that do? And what sort of things that we care about is that going to cause? Think about the whole system we've been talking about. Just keep this in mind. This is going to be important as we go. So, diuretics can act in a lot of different ways, but they're almost always going to prevent something from being reabsorbed from the urine, so that instead more of it is lost in the urine, causing more water to also be lost in the urine. So we have different classes. So acetozolinamide is a proximal tubule diuretic. It blocks the reabsorption of sodium carbonate, and that causes a higher concentration of that in the filtrate, which is going to prevent water from being reabsorbed. Mannitol is an osmotic diuretic, which means what mannitol does is it just increases the concentration of mannitol in the urine. When you do that, then the concentration of the urine is higher, even when you consider everything else normally. So that's going to cause more water to go out. There are loop diuretics, and loop diuretics are generally blocking the sodium-potassium chloride cotransporter. So it's blocking the removal of the reabsorption of salts, sodium, potassium, and chloride in the loop of Henle from the filtrate. And so when those can't go out, remember, water follows salt. So since we can't reabsorb the salts, the water will stay in there because, again, it's more concentrated. Thiazide diuretics block the sodium chloride transporter, so in the distal convoluted tubule, so same thing. And then we have ones that block the action of aldosterone, and that is then going to prevent sodium and potassium reabsorption later. So we have all these different things that can happen, and all of these are essentially just increasing the concentration of the filtrate, either by putting something into it or by preventing something from being reabsorbed that then causes less water to be reabsorbed. And that is our kidney-specific section here.